on concentration and time. How can you determine the order? Well, one of them was our 14.1 worksheet, right? Calculate the rate of each trial or calculate the rate of each reactant to get the order overall. See worksheet 14.1, right? That's one way. Or you can graph concentration versus time. If that gives you a nice R squared close to 1, then it's zero order. Then try graphing the natural log of each of your concentrations versus time. If that one's a nice R squared close to 1, then it's first order. If you graph 1 over concentration versus time and you get an R squared close to 1, then it's second order. So those are the two different ways was graphing that experimental data. Either one was from experimental data. None was from just looking at the equation. Or what we did on 14.1 and calculate the rate law and add up your exponents. Okay, then we started to use our integrated rate laws. So the first one is this reaction has a rate constant of this. So from the units, I know that it's first order because our K, remember the molarity goes down by 1. So if there's no molarity, it must be first order. I don't know what I'm doing yet. I just know that this is first order based off of those units. How much time? Okay, so I know I'm going to use one of our new ones off of our note sheet because we're looking for T, and T is not in regular rate laws. It's in the integrated rate laws. So we know how much time, of course, in seconds, for our concentration to only have 28% left. So 28% would be your final, or the amount after time T. This is our integrated rate law if it's first order. So it's first order, we're using this one. You could use this or the rearranged one. You're going to get the same answer. So I just plugged it into here. If I want, you can take 28% of anything and have that be your final. I just decided to make my initial 1 and my final 0.28. I took the natural log of that, divide both sides by negative K, and you get 45 seconds. Any questions on 1? Or I guess that's technically 2. Okay, let's look at the second one, or third, I guess. Okay, it's telling you it's first order. And again, you could tell from this rate law units. We start with 0.25 molar. So that's my initial concentration. How much will you have left after 8.8 minutes? Well, we need to convert those into seconds to be able to plug it in. We're going to, again, use our first order rate law. And we know our initial is 0.25, and we're going to solve for X. They gave us K, and our time, we have that. It's going to be 528 seconds. Goes here, multiply, seconds on the bottom, seconds on the top, cancel. To undo a natural log, it's base E. So E raised to the natural log, blah, 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 that cancels the natural log. So you get X over 0.25, and then E raised to this number after you multiply. So you have X over 0.25 gives you this number, times by 0.25 by 0.25. So you will have 0.18 molar left, and it should go down, right? You started with 0.25, you're going to end up with 0.18 after 528 seconds. All right, we still know it's first order for B and C. So for B, how long? So we're looking for time. Here's our initial, here's our final. So if you had this much left based off this first order rate law, so we plug in initial, final, K, that we're looking for X. So just like number 2, and we get, it's going to take 760 seconds. The next one for 90% to have, you have to kind of read it carefully, for 90% to have reacted. So that's like 90% of it's gone. Yeah, Mary Lou?
Is there a reason you did 2 sig figs instead of 1?
For B?
For C.
For C, I did 2. Oh, I guess not. I guess it should just be 1. Yeah, good question. Oh, yeah, that's fine. You could have done 1 or 2 just because 90% is not really like a measurement. I did it off of the K value, but I don't think AP test would take off for that. So this was still first order. I'm going to start with 1, and then I'm going to have 10% left, or 0.1. But again, you could have had whatever you're starting with and 10% left on top. And it's still the same K for all of this. It's the same reaction. It's still the same equation because it's first order. So 3,400 seconds, or if you did 1 sig fig, it should be 3,000 seconds. The next one, we have second order. So we're going to use this integrated rate law. And we want to know how many seconds. So we're looking for time. If it falls from 1.5, so that's my original, to 0.1, so quite a bit. And here's your rate law constant. It's meters, meters, what am I talking about? It's molarity in seconds on the bottom, so it must be second order, which we already know, it says second order, but just another little like reminder. So I go ahead and substitute in my what's left, what I started with, my K, and I'm looking for time, and you get 3.1 seconds. And then the second one, they change, well, what if the K is this instead? Same formula, this is just different, and it'll be 93 seconds. Any questions on the front side of the worksheet? All right, let's go to the back. Oh, it looks like we're going off the same one. There's a C and D. So here it's saying after 1 minute using this K, the original K that they gave you. I know that wasn't very clear, but the original K. Same rate law. We have 60 seconds, make sure it's in seconds, and we're solving for X on the denominator there. So you should have 0.0055 molarity left. 5 minutes, which is 300 seconds, same formula, looking for X on the bottom there, 0.0011 molarity. So the front side plus this was looking at the integrated rate laws using either first or second, making sure you know what each of your symbols represent. And then we went into half-life, which also depends if it's first order or second order. So when the half-life of a first order reaction, so that means it's not going to be dependent. Oh, sorry, I skipped one. How many half-lives have occurred if for a first order reaction when there's only 12.5% left? So if you have 100%, and there's 50% left, that's one half-life. 50%, half of that would be 25%, so a second half-life. 25 to 12.5, that's half, so that's 12.5. It took 3 half-lives to do that. First order, it does not depend on how much you have started with. Remember, a half-life is how much time it takes for 50% to be left. So it's like 50% of 50%. Okay, now this one's a first order. So natural log of 2, we know that as the 0.693. It's the same thing. So we know that 0.693 over your rate law constant is equal to your half-life if it's first order. So it said the half-life is every 35 seconds. It breaks down by 50%. And then we solve for K, and you get 0.020 seconds negative 1. It's a first order. So there should be no molarity, just seconds in the denominator. The next one is second order, same situation, but now we need this, right? It's dependent on that. So it's 1 over K, not the 0.693, and then your starting concentration. And we're going to solve for K. So I multiply both sides, divide. So 0.029, molarity negative 1, seconds negative 1 because it's second order. And then number 7, before we get to the graphing situation, a certain first order reaction is 35.5% complete in 4.9 minutes. So I got to change those to seconds at that temperature. Okay, great. That's room temp, so nothing funky. Because remember, K changes when temperature changes, but it's not going to go in any of our things here. What is the rate constant? So I know it's first order. I have my time, and this much has been consumed. So 100 minus that, 64.5 is left. We wanted, so the original, if I treat the original as 1, 35.5% of that has happened. So 1 minus that, or 100 minus that, is this. So if this much has been consumed or completed, you have this much left. So you start with 1, I did 0.645, or you could have done 100 and 64.5 or something, and 64.5 of whatever that is. There's my time, and I solve for K. What is the rate constant? So I get that. It's first order, so it's just seconds negative 1. How long will it take for the reaction to be 95% complete? So it's first order, and instead of 35.5% complete, it's 95% complete, meaning you only have 5% left. And I started with 1. Natural log of 1 is 0. Same here, natural log of 1 is 0. So then just look at this. And it would take over 2,000 seconds, 2,010 seconds to consume 95% of it if it's a first order, and that was your K constant. Any questions on those two before we get to the graphing? Okie dokie. Let's look at the graph ones. So our lab next week, this is the perfect warm up to that. So here it's saying, all right, I've got a bunch of data. So what we're going to do in our lab next week is there's a reaction with base that becomes less purple over time. So we're going to use the colorimeter because we learned first semester how to use light and get concentration. So every so often, we'll be getting concentration over time. Then we're going to graph time and your concentration, see if the R squared is close to 1. If that's not it, then we're going to do time and natural log of your concentrations. If that gives you an R squared close to 1, then it's first order. That doesn't work. Try this and natural log of each of these. Ours is going to be a liquid, so we're going to literally do concentration, and we know how to get concentration from light. This one happened to be a gas, so you can also use pressure interchangeably with concentrations because they're directly proportional. So we graphed natural log of pressure versus this, and 1 over pressure versus time. And we found, you should have found it to be first order. Your R squared should have been like 0.999 versus the other one was like 0.915. So close, but it's definitely first order. Great. So then it also says, what's the rate constant? So for first order, your slope is equal to negative K. So divide both sides by -1. And then your unit, since you know it's first order, should be seconds -1. Yeah. Questions on that one? The next one was why we zoomed through the last few PowerPoint slides. It's about activation energy. Oh, and we also have like I think a practice exercise using this 14.11, which is later on in your reading. But so we have temperature, change all of these to Kelvin. Then we're going to graph. So this is 1 over each of these in Kelvin. And then take the natural log of all your Ks, graph them. Get your y equals mx plus b. I got y equals negative 7,550.9 x plus my b. But really, this is what I care about. And what we learned on our PowerPoint, which is so cool, is you can solve for activation energy using this when it's in that y equals mx plus b form. So my slope is negative 7,550.9. So I'm going to set that equal to negative EA, which is what I'm looking for, over R. And we need to make sure we're using the 8.31. That was in joules, so I converted it to kilojoules, but that's fine if you left it in joules. I don't think it gave us which one to go by. You could have 8.31 joules. I did 0.00 to get it in kilojoules, but it's totally fine. I just divided my final answer by 1,000 if you use this, but it's fine. It didn't specify that it had to be kilojoules. So this would just be different where your decimal places. So yeah. That's the integrated rate laws and a little bit on activation energy. Definitely be graphing for our lab next week. And let's finish up the PowerPoint. Talk about the last part with rate law. Oh, and then so your lab will be due in a week. So on Fridays. We're going to have the lab pros due on Fridays. That way you have a little over a week from when you collected the data. We'll see each other a few times. You have questions, all that good stuff. So then the one we do Thursday, next Thursday won't be due until the following Friday. All right, I'm going to switch my camera up, share my screen. Whoa. Stop. There. Okay, let's share the screen. And so we started off with what our lab was yesterday and just kind of like what things increase collisions. The more collisions, the better. And we talked a lot about a little bit last class, how they have to not only collide, but with the correct amount of energy, which is our activation energy, and in the correct orientation. So whatever we can do to increase collisions, statistically is going to increase the likelihood of a successful collision. So we talked about concentration, temperature, all that good stuff. Then we got a little more quantitative, and that was our first worksheet on how we can discover the rate law. And we know it can only be discovered by experimental data, either by figuring out the individual orders by doing the dividing and getting that exponent, or from what we learned yesterday, graphing the certain things. And so you want to make sure you study and know what to graph for which order. There's only 0, 1, and 2 that we're expected to know for that. Okay, then the last part is like, well, why can't we look at the equation and why does it have anything to do with the stoichiometric ratio? That's what we're going to go into today and kind of end that chapter. And it kind of has to do with like it's not Hess's law, but like in Hess's law, you like get things to cancel and there's spectator ions. One of these things that maybe is 0 order could be a spectator ion. So we're going to look into that. All right, this did not go in a slideshow, did it? Okay. So a reaction mechanism, is the sequence of events that describe the actual process by which the reactants become products. That's called a reaction mechanism. So maybe it's multiple steps and we just see the overall step. So we're going to look at what's going on behind the scenes. What are those pre-steps? But we'll learn the actual vocab. So I think this might be blank and I didn't change the color on mine. But reactions may occur all at once. It may actually just be one step and the rate law looks just like your formula or equation. But usually it's through several discrete steps. And those individual steps that we don't see, they have a vocabulary term called elementary steps. And they're called like elementary reactions. So maybe there's 3 equations that happen that combine to make an overall reaction. So there's 3 elementary steps. And so some more vocabulary. This is different than the order. Like we said, first order, second order, third order. Now we're looking at mechanism. If in an individual step, not the overall step, there's one element, it's called unimolecular. There's just one type of molecule. And your rate law written directly off of that elementary step looks like this. If there's 2 things, whether it's 2 moles of the same thing or 1 mole of different things, it's bimolecular. And if you have 3 molecules, whether it's 3 of the same thing, 2 of one, 1 of the other, 3 different things, 1 of each, it's termolecular. And notice it doesn't go further than that. And this is not the order. People always get this wrong. When I ask for molecularity, that's this vocabulary. Order is first, second, third, and you can have a bunch. But when you have just like an individual step, like a elementary step, it's very rare to have over 3. I think it, sorry. I thought it said it on that one. Oh, it'll come up in a few slides, but it's very rare in an elementary step to have more than 3 molecules. So they're only saying like, we just need to know if that, go ahead. No, you're good. Okay. Okay. So maybe it takes 4 reactions to get our overall reaction, or 4 elementary reactions to get our overall reaction. We only care about the slowest step, and that's what our rate law is based off of. And it's called the rate determining step. Actually, is this on the same slide? Yeah. So this little picture they're showing is kind of like it's been a while, but when you drive to school and there's just that one light that takes forever. If you happen to get that light on a good day, you're going to get to school faster. Or if it takes forever, you're going to take forever to go to school. That's your rate determining step. The longest piece is your rate determining step. So if it takes 3 elementary reactions and 2 of them take 2 seconds and the other one takes a minute, the fastest, it can't go faster than its slowest step. It's kind of like its weakest link, but in timing. So we only care about the rate law of the slowest step, and that determines the rate. So that's called the rate determining step. And for sure on worksheets or things like that, you might see like RDS next to like a little reaction. And that's the one that's the slowest, and you're going to write your rate law based off of that. So let's look at a reaction. So here we have this reaction, NO2, they're all gases, NO2 and carbon monoxide, and you get nitrous oxide and carbon dioxide. The rate law for this reaction experimentally, just like we were doing first 2 worksheets, we have to have experimental data, was found to be this. On my notes, I have like experimentally. Okay. So it's found to be this. And it's like, well, wait a second. So then we know that CO does not affect the rate, right? It's like, oh, that must be zero order. And there's more fill-ins here. So CO, you need it for the reaction to go down, but it doesn't affect how fast or slow the reaction is. The rate, like you need it for it to go down, but it's not part of its rate determining step. It does not depend on the concentration of the CO. So this suggests that the reaction must occur in two steps. Somewhere it must need to make CO and then it's like consumed in the second step. So you need it, but it's one of the faster of the two steps. It's not our rate determining step. What was I gonna say? Yeah. So this was kind of like on our first worksheet, this chapter, that second one on the last one on the front sheet, we had, I think B was zero order. That suggests, oh, this must have a mechanism. It must be multiple steps. So we need it for the reaction to go down, but it doesn't affect how fast or slow it goes.
Wait, Ms. Portillo, where's that squared coming from?
Experimentally, we found the rate law.
Oh, right.
So they either graphed it or we did what we did on 14.1. They just didn't give us the data. They're just saying, hey, experimentally, we figured this out. So if they say, hey, this is the rate law for this, we can assume this happens in multiple steps. So a proposed mechanism or multiple steps could be, let's see if I can get, there we go. Something like this. When we add, just like Hess's law, if they're on the same side, we add. If they're across, like one of the reactants, one of the products, we cancel them. So do we see something that's on both sides? Is there anything that cancels out?
NO3.
Yeah, there's an NO3 on the products here and reactants here. We needed the NO3 for the reaction to go down. It's made in step 1 because you need it in step 2. It's made here, but then it's consumed here. So that's called an intermediate. I think we also have another intermediate.
NO2.
Yeah, I think the NO2. Yeah. Okay. The CO is, and then, okay, there's two steps that have to happen. So you need to make the NO3 so that the CO can react with it. Great. But the CO wasn't in our rate law, right? Here it is right here, NO2 squared. And that's because if you look at this one's our slowest step. So our rate is actually just dependent on this step. So this is an example where you can write the rate law directly from the formula when you have the mechanism. When they list multiple steps, find the slowest one, or let's say RDS, and you write the rate law. So this is rate equals K times, yeah, even though these might cancel, we're not, I was gonna say. You only do it if it's a product in the step and then a reactant on this step. So that was this one, cancel. So there's two NO2s. It's bimolecular for its molecularity, and it's second order for its rate law. Because if this one's fast, if step 2 or the elementary step 2 is faster than step 1, we only write the rate law for the slowest step. So we'll get to that. Was that a different reaction? Okay. So let's look at a completely different reaction and look at a mechanism. So the rate law for this reaction experimentally, they found is this. And this would be for, it's third, looks like it's third order, that's fine. But the molecularity, if this is an elementary step, it looks like it'd be termolecular, right? 2 NOs and 1 BR. And those are pretty rare. So it's also probably a 2-step. So there's something that is in your reaction that doesn't show up in your rate law. Or if you get something termolecular or larger, that infers that there must be a mechanism. There must be a multi-step process. So let's take a look at that. A proposed mechanism. So it could be something like this. We do have an intermediate. I'll tell you what this means here. These double arrows. So it's a half arrow forward and a half arrow back. That means these reactants are combining to make products. And those products are going in the reverse reaction and breaking down to make reactants at the same rate. So that means your forward reaction is just as fast as the reverse reaction. So step one includes the forward and the reverse reactions. So this one, we're going to go off our slowest step. So that's this one. Let's write our rate law based off of that. Rate equals K times NOBR2 times NO. Well, wait a second. NOBR2, that's an intermediate. It got consumed in that second step. So we're going to learn we're going to do a little substitution. And that's what our worksheet's going to look like, is writing these rate laws off your slowest step, and it's always your reactants. But if something shows up in your slowest step that gets canceled out, we're going to have to do a few extra steps. So the rate law of the overall depends on your rate determining step, the slowest step. And so we just wrote that would be rate equals K. They just wrote a subscript 2 to show is the K from the second elementary step. That's just like a label. But how can we find NOBR2 if that's an intermediate? Well, what we know is NOBR2 reacts two ways. And actually, I'm going to go back here. Step one, these two combine to make it. And in step two, the reverse would break up. But it looks like we don't have a reversible arrow there. So with NO to form NOBR, or it decomposes to reform NO and BR2. The first step we know are in equilibrium, because we saw that reversible arrow, I guess it was more like that. That means the rate of your forward, that's a little subscript F, is equal to the rate of the reverse. So whatever molarity per second the forward reaction is, the molarity per second is the same for the reverse. So we're going to do a little substitution based off of that. So since they're equal to each other, and we know that just by that, this arrow like that, what we can do is actually, I want to write it up here so we have it. I usually use the whiteboard, but let's do our step one. This was from like a previous slide. Our first elementary step was NO plus BR2 reversible, or at equilibrium, gives you NO BR2. And then our second step, elementary step, was the NO BR2 plus NO gives you, oh, no, that was not reversible. 2 NO BR. And this one's my rate determining step, and they told us that. So the rate law of this was, we found to be rate equals K. I'm just going to make a little 2 because it's from step 2. That's all that means. NOBR2, first order, NO. Well, we have a problem because this is an intermediate. So that's what we're trying to do right now, just kind of context. Okay, but what we know is, let me get a different color. The rate of the forward is equal to the rate of the reverse. So the rate of the forward of this reaction would be rate equals K for step 1, NO times, what was that, BR2. right? That's just the reactants of step one, nothing crazy. If we made the reaction go in reverse, the reactants would now be the products. And I'm going to say the rate is equal to, usually write a negative one, meaning it's the step one, but it's the reverse. And that would just be based off NOBR2. So this is the rate of the forward. This is the rate of reverse. Well, we know they're at equilibrium, so we can set them equal to each other. So this is going to take me a minute. I'm going to rewrite this where they're set equal. So I'm substituting the rate law for the forward into the rate. Okay, so we just defined what this is. So I'm going to go ahead and substitute my K constant, whatever that is, NO BR2. And I'm going to set that equal to my reverse, which was my reverse, whatever the K is for the reverse reaction, NOBR2. This is what we need to substitute for because that's an intermediate. So we're going to solve for this. So I'm going to divide this side by that K value, divide this side by that K value. And now NOBR2 is equal to NOBR. Now I'm going to substitute all of this in right here. Questions so far? Okay, it looks like this is.
You forgot the 2 on the NOBR on the right.
Oh, yes, thank you. And that's important because these get a little, like when you do Hess's law, it gets a little like.
And the one above.
Yes, thank you. Missed it over here. Nope, got there. Okay, I'm going to clear this because it's on your slide there, right? So this was the rate of the forward, the rate of the reverse. We're solving for this guy because that's my intermediate. And so you divide both sides by K. And you get this guy. And we're going to substitute that into our rate law that we had for the rate determining step, or that slowest step. So substitute in, I'm going to write my original law here. We had, what was that? Just NOB, yeah, okay. So for our rate determining step, just raw was like K, NOBR2, NO. We did some work and we found that NOBR2 using the first step is equal to K, oops, K negative 1, that's an equals. NOBR2. So we took all of this and substituted that here, and that's what this is. NO, NO, NO from here, NO from here, BR2, BR2, and then this is all the K values together, right? All of this and this. And NOBR2 is now not in the equation, but we know it's equivalent to NO times BR2 times some Ks. So we can substitute that in. And now we have an appropriate rate law that describes the slowest step without using an intermediate. Questions? Okay, we're going to consolidate. Let's see if it does that on the next. Yeah. So instead of doing this, we're going to make this to the second order. And I'm going to clear that out. Oh, there it is. And now your K constant, remember, these are just numbers. They're just different numbers. So it's like this number times this number divided by this number. That's just going to be the K for your rate law. So all those Ks can just come together and just be called K. It's just some number. And there's this guy and there's this guy. So this is the rate law for that. NO squared BR. Yeah, Mary Lou?
So like after it's in like that form, is that considered like the like final form or
That's the rate law. This is it. That's the answer. Jim?
So how do you get this if you don't have a reverse reaction?
You cannot.
You can't. If
Yeah,
you
because you
don't-
need to be, if there's an intermediate, but we'll learn in the next chapter that all of them are reversible, but everything on your worksheet should have a double arrow.
Okay.
So we're going to finish the power one. There's just a few more slides, but this is a good time to look at our worksheet for tonight.
For two, I just had one quick question.
Yeah, of course.
That's the rate for like the first step, right? What would the like rate for the like?
This is the rate for the slowest step. That was the rate we just solved for the rate of this.
So how'd you solve for the fast or step one?
We don't need it because you can't go faster than your slowest step.
Okay.
So this needs to happen and this needs to happen, but the rate's just dependent on the slowest one. So we're just going to write the rate law of this. So that's why before I was like, you cannot base it off of the formula because you don't know if there's some stuff behind the scenes like this, a mechanism. We write it based off the slowest one. If you're given the mechanism, then you can write it directly from that. So this, you find your slowest one and you can write directly the rate law. Okay, it's K times NOBR2 times NO. But if there's no intermediate, that's the rate law. But this guy, we cannot have that show up in the rate law. It gets consumed. So we had to go back to this one and solve for this and substitute that in here. Does that make more sense, Dylan? Yeah, Mary Lou?
quick refresher, how do we know which one's fast and which one's slow?
It'll tell you.
Okay, that makes it
It'll say
easy.
slow or it'll say RDS. So speaking of that, let's take a look at the worksheet. Okay, so let's blow this up. All right, so they're like, okay, elementary steps are added to give the overall reaction. So you've got these two elementary steps. And the molecularity, that's the number of particles in that step. It's rarely higher than 2, right? This is uni, this is uni. Just that's only elementary steps. All right, and then if the intermediate is a compound that's formed and then used up. That's why the other one, like if it was a Hess's law, I'd cancel. But in this, it's not considered an intermediate because it wasn't made in the first step and then eaten up in the second step. If an intermediate appears in the rate law, use another elementary step to solve for the intermediate and substitute. All right, so if we look at number 1, it's saying derive the rate law. So that's what we just did. We derived the rate law. If step 1 is your rate determining step. So you'd write it here, right? So rate equals K times A, right? Just the reactant. Is A an intermediate? Nope. So that's it, good to go. Now step 2, let's now back up and let's pretend this one's the slow step. Rate equals K times B, right? It would just be based off of this one. Is B an intermediate? Yeah, it's made in step 1 and then it's consumed. It's gone. So we need to solve for B. So this one has a double arrow and that means the rates are equal. So that means K1 times A is equal to K negative 1 times B. Does that make sense for that part? How semi-equal? Okay, I'm going to solve for B. So I'm going to divide this side by negative K, and now I'm going to substitute this in here, and it becomes rate equals K times A. because all of these Ks just become a generic K. It's just a bunch of numbers.
Sorry, Ms. Pritzio, how'd you know if like it was if it was an intermediate, like if an intermediate
An
appeared?
intermediate appears, oh no, not that. It is, that's not what I meant today. Oh, here it is, the one above it. An intermediate is a compound that's formed. So this side is formed, right? Your products. And then used up. So the first step happened and we made it. Then we consumed it to make C. So that one is intermediate. Versus A was made, but it was never consumed. Looking at it from this lens for this worksheet. And so that's what you're doing for these. And then the last one, though, you'll get some practice, Say this is your rate law. Now you tell me some elementary steps or a mechanism that could work out for that. So this one's a good little challenge one, this one and this one. So we'll play around with it. I would do that last because you want to get some practice and start seeing these. What you're coming up with for those is what could add up, what steps could add up to make this, or to get an intermediate where you could substitute and it looks like this. So it's going to take a little thinking. Give that a shot. Okay, just a few more. Yes, Dylan. Yeah, we meant to go like, oh yeah. Sounds great. I love to be challenged. Yes, yes.
Absolutely not.
Oh my gosh. All right, we're almost done. So let's finish this up and then I'll take any more questions. We did this. Okay. So to kind of finish up this PowerPoint, the talking about the speed of reactions, we talk about all these different things that could speed them up and slow it down. And we mentioned catalysts. And in that our little sophomore video, it was the matchmaker. Wasn't a reactant, wasn't a product. It just helps the reactants find each other. So if we use that in chemistry language, how does the matchmaker work in chemistry? And we talk about how they're really expensive and usually rare earth metals like, platinum, gold, things like that. So there's a lot of research into finding cheaper catalysts. Okay, so a catalyst, what it does is it increases the rate, makes it go faster by decreasing the activation energy, which we saw that sophomore year. We'd see like I would show you, it wouldn't look like a double dip like that, but I'd give you like a worksheet that had these potential energy diagrams is what we called them sophomore year. And I'd be like, oh, okay, the solid line is without a catalyst. And you'd see something like this and okay, that's a catalyst, right? It brings it down. Well, how it does that, let's see if it's on the slide. It changes the mechanism. It changes like one of those elementary steps behind the scenes to make it go a little bit faster. It's like taking an advanced mini golf course and making it a little bit more easy. But in chemistry wise, it's finding a different mechanism for that to go down. And you look more about this in maybe like AP Bio, you look at some of these catalysts because in the body, they're called enzymes. So one way a catalyst can speed up a reaction is by holding the reactants together and helping bonds to break. So, we'll see it on the next one. So this one's like, oh, here's two reactants, hydrogen, some sort of hydrocarbon. This is like your enzyme or your catalyst that kind of holds in there. And that's what like platinum and palladium and gold can kind of do. So like the not ones that are in your biology class, this would be more like inorganic or material science kind of stuff. And then they help find each other and boom, they go off. In our body, we have a lot of catalysts. There's so many and there's such a study on them. They're called enzymes. And there's all sorts of stuff, a physician or a microbiologist or things like that work on them because we want reactions to go faster or slower. Things like digestion would take us years, which we would be more like a sloth versus what we are today without enzymes to help it happen over a matter of hours. So enzymes, that's a catalyst in a biological system. And so I feel like this used to be called the lock and key method, but I guess they've changed this. Anyone who's taken AP Bio, that's called something else now, I think. But this, anyways, these words kind of trigger me like substrate, enzyme. I just remember this little situation. Anyways, so that enzyme, as chemists, we think of that as a catalyst. And then in biology, they just go, more in depth on the ones that happen in biological systems. So yeah, that's rate laws. So our next lab, which I think the Sign Up Genius, I have no idea when these things go out. I cannot see them. I don't know. But you guys did great yesterday. What a day. Oh my gosh. And it wasn't a Saturday or Sunday. Like after I was like, it's like 4 o'clock. I'm like, this is crazy. So I'm like, even if it was crazy, it's still a win because it's not our weekend. Like, I'm like, yes. So great job, everyone. So again, that lab won't be due for a week. Let me know if you have questions. I'm going to be looking at your data tables, right? Title, numbered, a nice specific title. I'm going to be looking, you have to do a graph. So figure 1, blah, blah, blah. What are you graphing? Units, all that good stuff. A good detailed method. So the procedures you guys sent me, right? Those were just procedures, not methods. So I was just kind of seeing that you knew what's going on. Yes, yes. Past tense, you telling me all the equipment you use without using you, I, me, we. Not talking about calculations. That comes into the results section. Okay, so that's that one. The one you're going to sign up for this week, whenever that drops, I'm not sure, that's going to be the one we're going to use the colorimeters again. So it should be pretty straightforward. It'll just be a lot of graphing at home. So that one will be nice. So you'll make your dilutions. We'll take our absorbance. And then we'll take, this one you'll need a flash drive because you're going to do a little reaction in the cuvette. You're going to set the cuvette and you're going to set up the LabQuest to take data like every like second or like 3 seconds for like 3 minutes. So you don't want to write all that down. So you'd put a little USB or flash drive in and we can just drag it. And then you could share it with, if you're working with a partner, with your partner. And then you can just copy and paste it into Excel. And then I'm going to show you a function that you can do a natural log of the whole column and just press enter. And then 1 over the whole column, just press enter. And then you'd highlight 2 of them, graph it, highlight the other 2, graph it. So we'll go over the Excel stuff after you just collect the data. But the data collection shouldn't be too bad. It'll be your calibration curve. I'm going on. The longest is making the different dilutions for these kind of labs, right? Then you just grab the data. And then the reaction itself is pretty fast. Just want to make sure you have a flash drive because it's a bunch of data. So most of the work will just be messing on the computer. Okay, and I think that's it. We'll go into chapter 15 next week, even though our lab will be part of 14. All right, any questions for me? Old labs, new labs, logistics, anything like that? All right, couple more outlines and this next worksheet. Let me know if you have any questions and have a great weekend. Thanks, guys.
Thank you very much, Ms. P.
Thanks, guys. Bye.
Ms. Bertio. Yeah. I didn't see the like the outlines and worksheet on the Google Classroom. Like it didn't show up until like today, like this morning.
Okay, mysteries.
So I was wondering if I could just like turn them in tomorrow.
Yeah,
Okay, sweet. Thank you.
Yeah, bye.
Definitely not like pulling a Roger or anything.
All right.
I'm not. I swear to God. Don't send.
No, it's all good. It's all good.
Don't send a mean email to my mother.
No, I won't.
Okay, see. Thank you.
Yeah, bye.
Yeah, Ms. Bertil.
Yeah.
So I just get a little confused about the K that's you get in the step 1 and step 2.
Yes.
So like in the worksheet, the first one you said, like the second step, you also get a K. Is it the same K as the
No, it's a
first
different
one?
number. Like let's pretend that let me annotate here. So let's do this one because this one had the substitution, right? So let's say a K is different for every reaction. So let's say the K for this, the forward is like 5 and the reverse is 2. I'm just making up numbers. And then for this one, the forward is 1. No, I'm going to make it easy. I'm just going to make it 1. They represent some number that we know. So when we do K times A is equal to K negative 1 times B, this is like a number 5, and this is like the number 2. So I divide by K. It's really like 5 divided by 2 times A. And that just represents another number, 2.5. But let's say it's that, and then we substituted that into, right, then we just have like K2 is equal to rate.
Yeah.
Well, K2 equals 1. So they just actually 1 times 5 over 2, that's just the new K.
Okay, so for the B, do we need to write that bunch of K, like K2 times K1 divided by K negative 1, that stuff?
Yes, when you're solving for it, you do, because AP will want to see that. But then when you box your final answer, just make it K.
So
Just consolidate the
the
K,
final
K.
answers, the rate law will be just a small K,
Right.
not the bunch of K.
correct.
You
But they
don't
do
have
want to see the work, if that makes sense.
So do we need to like identify like the final K, or
So this
just
is what you need to do. You would need to do, so say B was on the AP test or my test, right? You would write K subscript 1A equal K negative 1B. And then it's like, all right, let's solve for B. Or actually, and then on the side, you'd actually have the, oh, we looked at this rate law. It'd be rate equals K2 times B. Okay, well, that's an issue because that's an intermediate. So then I'm going to, I'm gonna use a different color. Divide. And then you get K1, K negative 1 times A. This should have been a B, by the way, equals B.
just substitute?
And then we're going to substitute K1, K negative 1, K2 times A equals rate. And then the one you would box would just be K times A equals rate.
Okay.
A lot of work for that, but they want to make sure you just didn't write that. You know what I mean? Like, oh, okay, you know how it goes.
Okay. Yeah, I just too much K, too many K.
I know. Hey, get ready. We learn about a capital K in the next chapter.
God.
I know there's a lot of Ks.
Okay.
But
thank
just,
you.
yeah, you're welcome. See ya. Have a good weekend.